Siemens is the leader in the development of smart manufacturing and the digitization of the manufacturing process with the digital twin concept. The addition of the Valor products helps bring this automation and efficiency to electronics manufacturing. Valor Process Preparation provides a complete analysis, modeling, and simulation environment for maximizing the efficiency of the design to manufacturing flow. The use of ODB++ allows a single data source to be utilized throughout the manufacturing process. The final PCB can be described with a single container for all common data, regardless of the various machines and outputs we need to support. This establishes a single point of truth that all process collateral can be created from, regardless of the machine being used. Board, part, and package data is common. If we are able to use a single application to manage all PCB assembly collateral, we can accelerate the MPI times as we only need to perform each task once. This eliminates redundant steps as well as increasing efficiency through automation, learning libraries, and the use of templates. When products need to be moved from one facility to another, usually the MPI phase needs to be repeated. However, Valor Process Prep can deliver the same common data set to the other factory so that they don't need to perform the MPI steps again. Valor has developed a central part and package library that describes manufacturer part number specific information, which can be used by Process Prep as a source of pick-and-place machine-specific parts, inspection parts, assembly documentation, stencil design, and design for assembly analysis. Process Prep can load from many different formats. Here we see the unloaded PCB, the assembly that contains the BOM, and the project that contains the panel. Let's look in more detail at the BOM using the part number for each component. Additional manufacturing data can be imported to the project that will streamline the creation of the manufacturing collateral. For example, this can be test attributes needed for ICT or SMT machine preferences. After reviewing the BOM data, we can look further at the PCB information. As we have use of the intelligent ODB++, the detailed properties on each component are available from the source CAD. The assembly plan defines the machines that will place each component on the board. Most components are placed by automated SMT equipment and are listed in the SMT assembly category. Odd form components will be placed by humans and defined in the manual placement category. Process Prep makes it easy to visually see the components placed in these two common categories. Here we see the automated machine placed components in green and the manually placed components in yellow. Next, we will create an auto assembly session where we can create files for the pick and place machines, as well as the optical inspection machines. Here we will step through the wizard that will do this for the ASM machine and the Viscom AOI machines. There are 4 steps to the auto assembly session. The first of those is the library parameters. Next step is assigning the parts to the placement machines. Third step is virtual sticky tape, where we check the placement of each component is correct as well as correctly oriented. Here, each placement can be visually checked against the board and silk screen to make sure the resultant program will have the correct position and rotation when placed by the machine. The final step is NC generation, the creation of the outputs for each machine in the auto assembly line. As a final step, we will get confirmation that the collateral has been created. Furthermore, this process prep collateral can be reviewed on the vendor software. ASM is the machine vendor and C-Place the software used by ASM machines. Here we see the resultant output from process prep being shown within the C-Place software. All placement and part data is available now in C-Place, significantly simplifying the final step of creating the ready-to-run program. Now we will create the collateral for the manually placed components. The manual assembly session allows us to define the number of stations we will need to place the required number of parts in the beat rate of the line. In this case, we create 2 manual stations where we will split the manual components across these 2 stations. Now we will go ahead and create the actual work instructions used by each of these stations. The work instruction documentation is easily created by applying a template to this design data. This creates consistent documentation for manual station people to act on. Next, we will create the stencil data using the stencil session. This uses technology to define the specific apertures on each component that needs paste applied to them. Once each footprint is approved, the rules are applied across the whole board to create the final stencil layers for the design.